Hello again, gentlemen. I'm going to do a little lesson on induction today, and I want to do this as a video just because there's a few demos I want to do that I don't think will turn out quite as well if we do it during the live class. So here we go. Induction is the idea that if you have a piece of metal, if you have a piece of any conducting material, if you generate a magnetic field inside of that conducting material, the material doesn't like that. It doesn't like change in magnetic field inside of this area. So, for example, if I take a bar magnet, this is this is the south side of the bar magnet. So magnetic field lines point away from the south side of a bar magnet. If I take this and I bring it really close to this, it doesn't like that. It doesn't like having a magnetic field generated inside of that area. Because it generates a magnetic field, this conducting material will try to negate the change in magnetic field. It will try and make a current happen inside of it that will generate a magnetic field in the opposite direction. So in this case, if we take, again, the south side of a magnet and we bring it really close to this loop, what happens is that it's generating, the magnet itself is putting magnetic field lines this direction through the loop. So the loop is going to say, no, I want to cancel those out and make magnetic field lines in the opposite direction inside the loop. So in order to do that, it has to make a current, and it has two options. It can make a current this direction, but if it does that, the magnetic field will be in the same direction that the magnet made, making the magnetic field even bigger. So it doesn't want that. What it wants is it wants to generate a magnetic field line, a current that generates a magnetic field in the opposite direction. So the total amount of magnetic field inside of that area is still the same as it was before. In other words, nothing. So again, no magnetic field in here right now. I bring the south side of a magnet close to this loop. Because I brought it close to this loop, there's now magnetic field lines going this direction in the loop. The loop's like, nope, I don't like that. I want to make magnetic field lines in the opposite direction. And the way that it generates current to do that is it needs a current that goes this way around the loop, and that generates a magnetic field that cancels out the added magnetic field. So by doing that, just by bringing this magnet closer, I'm generating a current inside of this loop. So I want to show you some examples of that. So what I have here is a machine that's really, really, really good at making strong magnetic fields. It's got a solenoid down here, and a solenoid, again, makes a magnetic field inside the solenoid. And inside that solenoid, there's an iron core, which is really good at transmitting magnetic fields. So this iron core will have a very strong magnetic field in it. So when I turn this thing on, again, you won't see anything, you'll hear something, but what's happening is a lot of current is traveling around there and a really strong magnetic field is being generated inside this tube. So what happens then if I have, and the magnetic field is strongest closest to the solenoid and it gets weaker as it goes further away, and you'll see that in a second. So what I'm going to do is I'm going to take another solenoid, and this solenoid I'm going to attach to a light bulb. It's attached to a light bulb already. So what happens is when this thing generates a magnetic field, it generates a magnetic field inside the tube. This guy is going to have, if I place it over the ring, it's going to have a sudden magnetic field generated inside of this solenoid. This thing doesn't like that, so it tries to generate an equally strong magnetic field in the opposite direction. But in order to do that, it has to create a current. So what happens is, when I turn this on, and this is going to be quite bright, when I turn this on, the light turns on, despite the fact that there's no connection here. That this is nothing, but if I put it over here, light turns on. And honestly, this feels a little bit magical sometimes, because there's no connection between these two. All that's happening is there's a magnetic field, and as the magnetic field is added inside of the ring's like, no, we don't like that. I need a magnetic field in the opposite direction, and because of that, it has to generate a current, and that current generates power, which is able to light the light bulb. So, one more time. If I turn this on, magnetic field generated in this direction. This then says, oh, well, I can't have that. Generate a magnetic field in the other direction. That creates a current. The current lights the light bulb up. Boom. Now, I've been shortcutting a little bit here because it's not quite that simple. This is just directly plugged into the wall, and therefore it's alternating current. So what's actually happening is the current is going one way, then the other way, then the back and forth, back and forth, back and forth, which means the magnetic field here is going back and forth and back and forth and back and forth and back and forth. And as you guys may know, our circuits in the wall run at 60 hertz. So every second, the magnetic field is flipping back and forth. It's going from here to here to here again 60 times, which means that inside this circuit, there's a constant change in magnetic field. It's changing back and forth, back and forth, back and forth. So it's generating the same alternating current in this ring, which again lights the light bulb up. So what then happens if instead of a light bulb, I just have a plain old ring of wire? Well, let's go back to the simple case. When this is generating an upward magnetic field and this wire's here, the wire is going to be like, I don't like that. I want to generate a magnetic field pointing in the opposite direction. What happens when you have two magnetic fields pointing in opposite directions? In other words, if I take two north ends of the magnet and I push them together, they repel each other, right? So in this situation, the same thing's going to happen. When this is sitting here, magnetic field gets generated upward by the machine. This thing says, no, I don't like that. Generates a downward magnetic field. When two magnetic fields are pointing at each other, they repel away from each other. Here's what happens. Jump straight off. If we start this up here, it just sits here, hovering. Like so. There's another mode on this one which does an even sharper burst. It increases the current quite a bit. And so if we go really quickly, this thing basically hits the ceiling in my house. So one more time. There we go. I'll do it once more. This is the exact same thing, but this time this is a little bit heavier. So again, this just sits here floating like this because it's always making a magnetic field that repels the magnetic field from here. Now, I can push this down, but if I do, this thing heats up really, really fast. Already, just from that, this is hot enough that it's like uncomfortable to touch. It's not painful, but it's uncomfortable. Because I'm doing a lot of work on this thing. I'm pushing against the magnetic field. So a lot of energy is being soaked into this ring, which heats it up. All right, but now we have another ring. But this ring, as you can see, it has a tiny little slit here. This slit does not allow current to flow around it. So because current can't flow around anymore, we're not going to this thing cannot generate a magnetic field. So if I put this on here and turn it on, nothing happens. Doesn't matter. There's nothing, like it doesn't float, nothing. If I go on the jump setting, nothing happens. Because a current cannot float, because a current cannot run around this ring, it cannot generate a magnetic field that counters the magnetic field that's here. So this is kind of the principle of what's called induction, basically. When you generate a magnetic field inside of a ring, the ring says, no, I don't like that, I don't want it to happen, and generates a magnetic field that cancels out the change. So this one has a magnetic field. If I take the south end of a magnet and I generate a magnetic field with magnetic field lines this way, the ring says no thank you and generates a magnetic field in the opposite direction to cancel it out. Using the right hand rule, that means a current will be flowing this direction around the ring. Excellent. That's induction. That's the basics of induction and why it happens and some of the principles of it. Next class, we're going to go over some of the equations that govern that and the amount of current, the relationship between the amount of current, the strength of the magnetic field, and the area of the loop. And once we've done that, we'll have a much better understanding of induction, how it works, and some of the applications of it. That's it for this video. Hopefully that was helpful. We'll see you next class.